Well, so today is the last lecture. Wow. It's been an interesting adventure. And so what I wanted to do today is give you some sense of the things we didn't have time to talk about. Some of the other topics you can apply these ideas to. Mostly what we've been presenting has been sort of introductory computational mechanics. And then also to mention some of the ongoing research projects. But mostly this will be kind of like a newspaper story. I mean, I'm just going to go through a couple different projects, spend some time mentioning current results or places we'd like to go, some of the interesting problems I think that are tractable or maybe intractable but important to figure out, and I still have no clue. So it'll be kind of a smorgasbord of different topics, but hopefully it will give you some sense of the breadth of applicability of these ideas and their relevance. But before we do that, I just wanted to remind us where we've come from. Remember, we haven't seen this diagram in a while. I was kind of putting it up every few weeks in the winter quarter and the beginning of spring quarter to kind of remind us, but we've actually, that's it. This is the course, right? This is the learning channel. We did the whole thing. 20 weeks, 2 quarters. If you remember, way back when, we were talking about nonlinear dynamical systems, and the motivation for that was how rich can nature be? And over the last century, there's been this explosion in techniques and appreciation for how rich and complicated nature can be. And going back to Poincaré in the 1800s, late 1800s, this development of these ideas, mostly nurtured in mathematics of qualitative dynamics for these nonlinear systems that you cannot write down in closed-form solutions. There's still ways we can come to understand how they're organized and how they're structured. And so that, of course, just flourished, and it's a very active discipline now, aerodynamical systems, with just hundreds of applications. In fact, these days, it's almost like the field isn't even notable anymore for being something you point to. It's used so broadly, whether it's population dynamics, evolutionary dynamics, the highly excited electrons and cold atoms, superconductivity. It's just all over the map. Chemical dynamics, population dynamics, dynamics of the social web. It's just very, very broad. And so in a funny way, it's kind of got taken up so much, people kind of forget that it's this unitary set of ideas with this long, century-long history. So, so we had invariant sets, invariant distributions, notion of attractors, attractor basin portraits, bifurcations, how all that qualitative behavior changes a functional parameter. So that can constitute that. And then, of course, we close the box, kind of. And it was really a principal kind of theme that we explicitly acknowledge that we don't have direct access to the natural world. We obviously have some access to it. Otherwise, we wouldn't be here. But it's always indirect, right? So that was formalized in terms of this notion of an instrument, that we just have some very impoverished. Maybe we don't sample fast enough, maybe we don't have enough accuracy for the scalar signals, maybe it's a spatially extended system, but we can't probe every spatial point, so we just have a few spatial points, and so on. Those are sort of limitations characteristic of every experimental system, and so that presents this question. Well, first of all, are there good instruments? So we talked about those, very restricted Markov partitions, where in some sense the individual symbols labeling these regions of the state space really are picking up the effective state of the process. But the more typical case was represented by the generating partitions, where there's some information that's spread out over sequences of measurements. And it's just kind of surprising that, and a wonderful thing, that the symbolic dynamics and this coarse partitioning works for continuous systems, particularly when they're chaotic. Right? And the idea there was, we studied in a dynamical part this kind of Lyapunov exponent dot spreading picture, how there's this exponential sensitivity to initial conditions. So there's always spreading of trajectories exponentially fast in forward time. Well, it was exactly that property that allowed measurement sequences to, in a sense, infer backwards smaller and smaller subsets of initial conditions that could produce a particular trajectory. So they sort of go hand in hand. The effectiveness of coarse graining comes from the system being chaotic and unstable. So the Lord giveth and the Lord taketh away. So it kind of balances out. Then we ended up with this thing that we call the process. In some ways, kind of left behind, even the fact we had an instrument that we were peering into this high-dimensional, possibly high-dimensional system. And we just then had to describe these stochastic processes, complex stochastic processes. I kind of argued that one useful way to look at them is how they store and process information. So we started out with basic information theory, and kind of soon realized that even though it's a field that's very rich, in the textbook we use, Elements of Information Theory from Cover and Thomas, is 600-some pages, the model class that they assumed there was IID, which was exactly what we didn't find interesting because there were no correlations, no structures, we came to call it. So we had to take the ideas and motivation from Claude Shannon in the 40s and his disciples and extend those to deal with complex temporal processes, to deal with correlations and structure over different time scales. So that led us to a whole series of different measures. So one lesson there was information is not this unitary thing. Information is contextual, and it's always an answer to a question. How much information is produced? Well, that's the answer. That's the entropy rate. How much information is stored? Well, we realized that was a little bit kind of vague. We didn't actually answer that until we finally got to the end here, but at least within information theory, we use the past-future mutual information, or excess entropy, as a proxy for that. And I ended up sort of suggesting we call that the apparent stored information, the information in the observed sequences. How much information to synchronize? How hidden are processes, the crypticity, and so on. So we started talking about these other measures. And then finally, noting the kind of limitations of information theory as it just focuses on measurement sequences, we started talking about modeling more directly, which in some ways is where we should have started, right? But this is a series of questions we're being posed as we sort of move along the learning channel and finally come to this notion of, well, how do we model things? And in particular, how do we ever remove the subjectivity of modeling? So the proposal was this sort of generalized notion of effective state, or the causal state, and that led us to the epsilon machine. And a number of uses of that, not the least of which is to answer the question, how much information does a process store in the present moment from its past? So that was the statistical complexity, and that was distinguished from past-future mutual information. And then the puzzle there was this observed mutual information, shared information from past and future, is not the stored information in the process. You can have something that looks very close to a fair coin with E close to 0, but lots of internal structure. So that makes us sort of a little cautious as we do sort of too simple analyses of just measurement sequences. You really should be thinking about what the effective states are and trying to infer some model first. So the algebraic structure of the epsilon machine captured the symmetries and partial symmetries, gave us a notion of patternness. We can measure the degree of patternness with the associated amount of statistical complexity or stored information. This number, statistical complexity, only makes sense, though, when we have a presentation where that we can prove is minimal. Needless elaborations would allow more and more state information that the process doesn't actually use. So the predictive equivalence relation led to these causal states, the notion of effective states, and then from that we actually derive the minimality of the causal states and the optimality of the epsilon machine. So we can associate numbers like stored information, statistical complexity with the epsilon machine, but really when we talk about how patterned or structured something is, it's the epsilon machine itself, the states of transition structure, the full answer. There's still a number of questions here about how to infer epsilon machines, do that consistently. I guess at this point what I've done is motivate that we really, if you're going to do any scientific analysis, this is the outrageousness of the claim. If you do any kind of statistical modeling, really what you want to do is first get the epsilon machine and then calculate properties from it. Or the other way to say it is, even if you're doing simple sequence analysis out here, you in a sense already have a model stuck in your head. A lookup table of sequences. You're doing a frequency count of how often the words occur. That's a model. That's a histogram model. So why not just jump in and say, look, the first thing we have to do is think about the process of modeling. So, and because of the very nature of these questions of what is information and what is structure, the reason that I organize the course this way is I can't, I mean, I could say the basic ideas in a few sentences, but I don't think one gets a real appreciation for the kind of depth and also the interdependence between these ideas. You can't just talk about randomness unless you're talking about structure, right? If you miss how a process is structured, you can't develop a good measure of how random it is. And, I mean, I say that makes sense now after all these weeks, but in fact, there are large literatures out there, whether it's in theoretical computer science, statistics, talking about what randomness is, with not once saying how the processes they're talking about are structured. It's just a mystery. It's not, these questions can't be done on their own. So that's sort of one of the kind of main lessons here. You sort of, I feel like you sort of have to have all these different issues on the table all at once, and then you step back and see how they're related. Okay, so this is sort of, a pipeline in a way, kind of analysis pipeline or a view of the world. It's a theory of how we build theories. And I don't, despite maybe some simple statements I make, I'm not implying that this is complete. This whole picture here is complete in certain important ways. I'll talk about some of the research topics that'll make that concrete. But also, just the little quick introduction we did, dynamical systems, didn't exhaust that theory. We didn't really talk too much except today on cellular automata, map lattices, on spatial pattern formation. We didn't talk about quantum machines. There's all sorts of stuff we just didn't cover. Wasn't enough time. But now I think if you looked at those kinds of problems, you could think about how you could take these ideas and start to understand spatial pattern formation, how much information is stored in a spatial pattern. At least those questions now start to make some sense. Okay, so now for the kind of newspaper story part of this, I just wanted to at least go one or two radii out from the ideas we talked about. Things that, given another quarter, or maybe longer, we could have covered. Some of these things were mentioned. So how epsilon machines, they can be enumerated. I'll talk about that a bit. We didn't really talk about infinite epsilon machines beyond the simple non-unit Feeler source. So we'll talk about that. There's also this really interesting question about, when you look at nature has these different scales of organization, right? Classic stories we have. Quarks, gluons, nucleons, electrons. Oh, we make atoms. Oh, we make molecules. Oh, the molecules form together and make larger molecules, macromolecules. Those become biologically active and store information. We call that DNA. Some of that codes for things like membranes, two-dimensional molecules. Those are cells. Cells get together. They have organisms. They compete against each other. They go to war. They build the internet. There are all these different levels of nature that we see. In fact, it's almost this kind of hierarchical structure I'm talking about. It almost defines the different disciplines. And there is sort of a question, maybe a little bit begged by the sort of fundamentalists in physics, namely that all these other levels are sort of irrelevant. The only thing that's important are the fundamental forces of the particles, quarks, and the standard model, and so on. Of course, anyone outside of that group tends to think that's ridiculous. They think when they're studying evolutionary biology, they're really interesting, unique questions that very most likely don't actually involve quark physics. So, and there's kind of a tension. It's I'm being a little bit facetious here, but there's this kind of tension between, are these new levels in the hierarchy fundamentally different? Is there, in a sense, a new physics at each new level? Or is it always ultimately derivable back down to the basics? Well, of course, if you're the folks, these fundamentalists down in the basement, you think that's the most important thing, but the rest of science kind of tends to disagree. So there's a really nice article by the Nobel laureate Phil Anderson, written in the early 70s, and I think it was Physics Today. And his point, he tried to argue, and this was scandalous back then, that in fact these other levels really are new kinds of physics There are new emergent properties. They're different. They have their own rules. The objects that come out are sort of unique to that level. And you can have a very powerful and sort of concise, self-contained theory at these new levels. He's not denying that if you really rolled up your sleeves, you could go back down and describe ionic conduction in an axon in terms of quarks. I don't think anyone's trying to do that, although there are popular books that claim that consciousness has something to do with quantum chromodynamics, which I suggest putting that aside. But so this interesting issue of hierarchy. So in fact, the predictive equivalence relation I gave you is too simple. And so there's a way of dealing with hierarchical processes, sort of machines of machines of machines. Like I said, we didn't talk about quantum processes. We didn't really talk about other kinds of inference contexts. So Claude Shannon and his two amazing papers in the 40s that introduced information theory, he also talked about something called rate distortion theory, and how you can trade off different properties as you're doing modeling. He didn't quite say it that way, but coding for him. We talked about cellular automata and pattern formation, the dynamics part of the course, but I didn't really tell you how computational mechanics applies to discovering structures there. So we'll talk about that. Same thing with various kinds of statistical mechanical models in 1 and 2 dimensions. How do we build optimal instruments? How do we optimally partition? Is there some way of doing that? Or what's the characteristic of an optimal model? When I talked about Markov generating partitions, I had the function sitting there, the mapping, and so I could use various properties like, the monotone pieces, and then we put a divider for the generating partition below each extremum. But I had to know what F was, what the dynamic was. Is there some more empirical way of doing that? So I mentioned that. And then we have these tools that tell us how much information is stored, how much information is produced, how hidden systems are. Those are almost like the macroscopic parameters of 19th century thermodynamics, pressure, temperature, volume. We have these macro parameters, or mesoscopic parameters. So we can actually do surveys, what we call complexity entropy diagrams, sort of like doing steam tables for water or whatever else. We have these other properties, macro properties, average properties. Okay. So first topic, and Chris Strelioff used this when he was talking about the Bayesian inference. He mentioned very quickly that epsilon machines, what we call topological epsilon machines, in a sense stripping off their probabilities, or the other way of thinking about it, the machines that just describe the sequences and the support of the word distribution can be enumerated. So, and part of this is trying to understand what's out there. So every process, well, we only pretty much just talked about stationary processes, so I could be a little more polite. Every stationary process has an epsilon machine presentation of it, kind of its canonical minimal model. Therefore, we can study the space of processes and how the space of processes is organized. How complicated can things be by studying the space of epsilon machines because of this mapping. And then in addition, we have this sort of notion of structure, the algebraic structure, topological structure, the epsilon machine, and borrowing some ideas from automata theory, we came up, in fact, it was Ben Johnson, a math student here, with a way of exactly enumerating these topological structures. So this was also Carl McTagg, actually Cambridge University Math Department. And here's one result. So we can look at the number of epsilon machines, topological epsilon machines. It's a function of the number of states and the alphabet size. Now we pretty much just dealt with binary alphabets. And you can see how horrendously fast this set of structured processes grows. And 3, if you have one state, right, we know what those are. Fair coin with 2 edges, all zeros, all ones, in case we have 3 of those. 7, 2-state, you can almost imagine writing those out, put on 2 states and making sure they're unifilar and all that kind of thing, and didn't minimize. But then suddenly, at 6 states, we have about 1 million, and at 8 states, due to Ben's new algorithm, there are about 2 billion of them.
You said that there were 3 different ones, so you count the one with the 0,
differently.
Ones.
Yeah.
Has there been any reduction of those numbers based on
Yeah.
those symmetries?
Yeah, you can add more symmetries to it, right?
Okay, just reduce
Yeah.
that.
So, for example, the all zeros and all ones processes would be equivalent up for the information measures because information doesn't care what the actual symbol names are. So you can have other classes like this. The other interesting thing, again, we didn't really think about this so much, just to keep things simple, but you can also look at what happens when you grow the alphabet size. So even if you're looking at the two-state epsilon machines, but they have a 6-letter alphabet, there are 250,000 of them. Of course, one way to look at this is go, oh my God, this combinatorial explosion. It's really complicated out there. I just find this fascinating. That things can be so diverse. I think the future will show that for most modeling problems, when you're looking at structure, probably practically, we're only going to be looking at a few state machines, up to 4 or 5 states, medium-sized alphabets, that kind of thing. Beyond that, we might want to talk about epsilon machines that are continuous processes. So, which we'll get to. So this is sort of quoting former Secretary of Defense Donald Rumsfeld. I see this table, or this whole exercise of, well, how rich is the space of stationary processes? Is trying to figure out the sort of unknown unknowns. What could be out there? To know them, if you can. Do this kind of enumeration and see how rich it is. And there's certainly ways to deal with some of this combinatorial complexity, like in the case of the Bayesian inference that was literally just looking at all 6-state machines and calculating their posterior probability for producing a given data. And that just returned a million numbers, these posterior probabilities. You can also do this incrementally and try to learn smaller models and have that prune as you go out. So we're trying to develop algorithms that don't consider all possible machines because you've already learned some structure up here when we learned, say, the 3-state machines that will prune out huge numbers of these bigger ones. So there will be more efficient ways to go to higher numbers of states and larger alphabets. Okay, now these are all of the finite state. Well, kind of getting large finite state machines. We just played around a little bit with the simple non-unifilar source as an infinite state machine, countable infinity. In fact, it's here. So what I'm going to show you, and this is just pictures to kind of make the point, if you randomly pull processes out of the space of processes, typically the mixed states aren't finite when you're calculating the causal states. So here they're countable, and you guys work through this in your homework. What I've done here is I added the SNS presentation as 2 states. Well, it's kind of boring if I had a 1-dimensional simplex, so I split one of the states. So now I have a 3 simplex. And then this is the reset state. When you see a 0, you know you're in state A. You're synchronized, therefore it's on the vertex of the simplex, the mixed state simplex. And then as you see more 1s, it kind of goes up towards this point up here. But just by way of contrast, it's more typical that the set of mixed states has some sort of, this is a 4-state presentation, non-unifilar. I actually forget what the transition matrices are, but so you get these weird fractally structures. In fact, Tuesday, Alex showed a couple of these more complicated things for the Mandel-Jarzynski model of information engines. And then it can be a full continuum, too. So we know these things exist, and there are a bunch of follow-on research questions. What's to measure here? If you go p log p over each one of these causal states, it's obviously going to diverge, so you need some other kind of quantity here. So we look at what's called the information dimension, the scaling rate of this to give it the sort of fractal dimension of the set. And that's the sort of rate of increased storage of information.
So I'm wondering if you can say anything about how common it is to have an infinite number of mixed states for just unifilar processes. So I guess with non-unifilar, it's kind of typical.
Well, I mean, this table are the minimal unifilar ones.
Okay.
So.
Well, how many, or how easy, like if you just took a random topology and then gave it, any one of these topologies basically, and you just gave a random probability distribution over the transitions, then like how likely is it that you have an infinite number of mixed states basically?
recurrent mixed states or total mixed states?
I guess total. I guess my question is basically, can we sync?
Yes.
You can have an infinite number and still sync.
Right.
Right.
And it does appear that infinite is very common.
Yes. Yes.
Infinite transient, not necessarily
Yeah.
infinite
Even as I summarize some of these areas, I'm leaving out whole sets of things. So it turns out you can have simple recurrent components. So we have been studying these non-ergodic processes, extended most of these ideas, where you have multiple recurrent components. And even if you have two biased coins, for example, 60, 40, 30, 70, something like that, you can have an infinite number of transients. So you have infinite number of transient causal states when the recurrent components have a finite number of causal states.
number. More interesting, the recurrent portion is infinitely far away from the start mixed state in that example, but there are ones with an infinite number of transient states, but the recurrent component is a finite distance from the start mixed state.
Yeah. So
These are all unified.
Yes.
Start.
You can start with machines that are in that table right there.
Yeah.
You get ones with, well, those ones, I believe, will all, the recurrence will be a finite distance away from the start. But there might be an infinite number of recurrent, in fact, for probably the vast majority of those machines. So we don't have an exact number, but it appears to scale toward probability 1 with
Yeah.
large machines.
Yeah.
That there are an infinite number of transient states.
Mhm. So they're hard to sync to.
Yeah.
Even if they have finite statistical complexity. Alec.
How difficult is it to calculate those numbers?
It's pretty fast, but that's a relative statement. Actually it was Carl McTagg, was an REU student of mine back at the Santa Fe Institute about 10 years ago. And we came up with some algorithms for doing this. We could only get up to about here, and that took, I had a cluster, Linux cluster at the time with 30 CPUs. It took a month. We can get up to here in just a few hours on a laptop now. So this new algorithm that Ben came up with is just a screamer. So it's pretty fast in a sense. I mean, if you wanted to go to 100 states, obviously that's not an
Do you
issue.
iterate through all the machines, I
Yeah,
guess?
yeah,
Okay.
yeah,
There's
yeah.
not.
It's
kind of, maybe that's just helpful for understanding. It's kind of you start with these, and then kind of take the three machines you have here, and they kind of form families that you then split out, and then you have the 7, and those kind of, there's a little bit of a tree structure here, which is what we're hoping to exploit for this pruning in the Bayesian inference. That's very much something we have to work on. So. Yeah, relatively fast. And it's all built into Campy, by the way. So you can, there's a library of these already pre-computed. You can kind of go back and forth. Each machine has a kind of a unique integer associated with it in the sequence, and you can kind of go back and forth from machine to integer. We're trying to come up with ways of, for example, maybe you can't enumerate the 20-state machines, binary machines, but maybe you want, I'd like a Monte Carlo sample of 1,000 of them. So we're trying to think about how to do a sampling algorithm. Okay, so yeah, lots of finite state machines with interesting properties, and we're talking about recurrent states there, not transients, even that, and then other kinds of infinite state machines. So, okay, so now this issue of hierarchy. So this is a little bit of a busy slide, but I just want to make kind of a simple point here. So recall the predictive equivalence relation. The idea was, so the question was, what are the effective states? I have some process. What are the effective states? And somehow by cajoling you or maybe arguing philosophically, we sort of came to this idea that what you should do if you're trying to predict the process is you don't make useless distinctions. In particular, you group all the histories together that lead to the same prediction. That's the statement of the predictive equivalence relation. So that's fine. But sometimes, like we were just talking about, you can have the effective states for a process can be infinite. So in some sense, one way to think about it is you made the wrong assumption. You were sort of starting off saying, oh, I think it's a finite state process, and I'm going to group these histories together, and I find if I have a certain amount of data, I have 13 causal states, and I throw more data at it, and now I can make finer distinctions. I see there are 22 causal states. I throw more data at it, there's 31 causal states, and it kind of keeps growing. So and this is the way we looked at, and was kind of, this problem first came up when we were looking at the logistic map at the onset of chaos. Remember that funny Morse 2e sequence? But it's
infinite state epsilon machine that you get there. So I got to thinking about, well, how can we deal with this? So what you do is it's the same kind of thing. Once you have this now infinite state model, you look at sequences in that model and over those states, and then form metacausal states using the same equivalence relation. So you kind of start out sort of at level 0. That's the data. In fact, we already kind of did this. In some sense, the instrument was going from state to state to state. We had kind of level 0, the prosaic states that are just the measurements. And then we group them into these, group the past in terms of the future morphs to get the causal states. Well, in fact, there was an intermediate representation. We went to a tree, remember the parse tree. And then we grouped and going from the data, what we did is we just put these all on all the sequences in a sliding window onto a tree. So we got this hierarchical picture of the word distribution, and then we applied another equivalence relation, the predictive equivalence relation, to get the causal states. And then when this level of representation diverges, you do the same thing again. You try to group things together and look at regularities. And it turned out for the logistic map, this is a 47-state approximation. So these are the causal states up to 47 of them for the onset of chaos symbolic dynamics, the Morse-Tui sequence. But in fact, you see there are these long, it's hard to see in this, but there are these long deterministic chains. So what you can do is you just replace all these individual states with a single edge with words on them. And once you do that, you realize that there's a very regular operation. It takes a word of length 1 to a word of length 2. Those are the Morse-Tui grammatical productions. And the state architecture becomes very regular. So then you call those causal states, and then you can write down what's called an index context-free automaton with a finite number of metacausal states that operates on strings. So there's a way of going from, in a sense, an incorrect finite state assumption. You look at smaller, less accurate models and how they get transformed when you, say, throw more data at them to larger, more accurate models. And then you ask, is there an operator that takes me from a smaller model to the more accurate, larger model? And then in the case of the logistic map onset, there is a single operator that does that, and that's these grammatical productions.
But yeah,
Yeah.
I was just going to ask more about the operator. It's just it's adding chunks of words to
Yeah.
whatever your state was that you were at.
Yeah, it's a little hard to see here. Maybe if you look at the slides online, I go from, let's see, 0 to 1, 1, or 0 to 1, 0. And there's one down here. Yeah, so, and those are the productions, and you just keep applying
How
those
is
things.
that different than the tree? Than doing the tree?
Well, in some sense, every one of these is, if you allow them to be infinite state, I have infinite data, I have an infinite tree, I have an infinite finite state, infinite explicit state presentation. They're all describing the same process. It's just I'm using this equivalence relation idea, higher level, more abstract, to keep trying to, so the overall rule is I keep going up this hierarchical level of presentation class, and I keep applying the same grouping idea, but to now the elements of the model, until it stops. And even then, you can imagine cases where it wouldn't even stop. So these are going up to string productions. There's some examples like the simple non-unifiedlich source you can represent as a few state machine that controls a counter. And the counter keeps track of the varying transition probabilities as you go down that long chain of ones. Other interesting issues come up, like, well, should I use this string manipulation? 0 goes to 1, 0, 1 goes to 1, 1 type of thing. A register, a finite state machine with a register that has strings, or a finite state machine with a counter that just counts up. So that's just an interesting open question. If we just stay within the kind of finite state case, then we have this measure. This is more complex because it's got 13 states compared to a 5-state thing. But once you move up to these infinite state machines or infinite state processes, the notion of a minimal presentation for it is ambiguous. I should use a stack, I should use a queue, I should use a counter, what? Now, using the causal states, that's fine. Again, they're all there. When I say stack, queue, and a counter, those are humanly constructed things, which when I say them, we immediately, it evokes a picture because we're familiar with them. there could be other weird devices too, so that's kind of interesting. What else could exist up at this higher level? Other strange devices that do, nonetheless, maybe interesting information processing. It's all captured in the state transitions and these effective causal states. At whatever level, it's there, but it may not be familiar to us. You know, we spent too much time programming in C. Therefore, we have certain idea, certain set of metaphors that are understandable to us, but there could be whole other kinds of high levels of computation. They're just not familiar to us yet.
Yeah, I was just wondering about that. Is there any parallels to the Chomsky hierarchy of
This is greatly stimulated by the Chomsky hierarchy. So the Chomsky hierarchy, well, Chomsky, some of you know, I mean, most of you know, he's kind of a leftist radical commentator these days, but his early days were in linguistics, and he proposed a class of different linguistic models using different kinds of grammars. He called them phrase structure grammars, and then made mappings from those down to finite state machines. It started basically one important part of automata theory and formal language theory. And it turned out his models of this as a model of human language, not so good. As a model of computer language, is spot on, and it kind of developed. Like every compiler and parser we use is kind of based on these ideas. So it's very nice, really work by him in the late 50s. In fact, it's interesting how he introduces the whole idea of this hierarchy of different computational devices, kind of in the scientific paradigm, trying to come up with theories. So he was trying to convince his linguistic colleagues that they should use mathematical representations of language, human language, and he appealed to, oh, this is sort of like how we build theories of the world. So anyway, it's interesting. Paper's 1958. Definitely worth reading. It's very interesting. So yes, so there's a direct parallel, except this notion of what I call hierarchical epsilon machine reconstruction, it induces its own hierarchy. So these would just be the lowest steps, and sort of what I was saying, it's a little bit of parallel to what happens in the Chomsky hierarchy. Because suddenly, when you get up to infinite state models, at least at this stage, we don't know that there's a natural linear ordering. So you get a partial ordering. Just like when you go from finite state machines, the Chomsky hierarchy, you step up to context-free languages and corresponding grammars, or push down automata, you move up to linear bounded automata, context-sensitive grammars, and finally at the very top of the Chomsky hierarchy are universal Turing machines that can compute everything below. So this hierarchy, I don't know what the upper reaches are.
But if you do find something that doesn't match it, then haven't you disproven the church Turing thesis?
There's some interesting questions like that, yeah. So you might say, well, why? What's the motivation for doing this again and again and again? And I think it's sort of interesting to realize that if I had an infinite amount of memory, or your computer did, you would never be compelled to come up with a finite model, right? I mean, if I can remember all of my experience as just raw data, then why build a model? So there's this interesting notion that it's actually having finite inferential or data or computational resources that actually drives sort of moving up from one level to another. It's because you don't have infinite resources that it's better for you to not have this infinitely deep tree, but the golden mean two-state process in your head. It's because you're too stupid. It's because you're too limited that it drives in the direction of more abstraction. Seems like an interesting twist. Your finite abilities actually drive you to be more intelligent. But this is very metaphorical thinking about this hierarchy. So let's keep moving on here. Like a newspaper story, we just might cut this off at some point. Maybe just very quickly, no surprise, you can also talk about machines for quantum processes. And since this is going to be just a one-slide summary, I can tell you what the basic idea is pretty quickly. So far, we've been using internal Markov chains with a transition matrix. Well, those classical states become quantum states, so-called qubits, and they aren't probability vectors over a simplex. They're probability wave functions on a sphere or on a circle. They're basically little oscillators. And then the transition dynamic, we go from, on the classical case, real numbers between 0 and 1 that sum to 1 to complex numbers that evolve this wave function forward. So you end up with, you can have kind of state-based representations of quantum process. So again, real crudely, you've taken finite state machines and you have to respect certain properties of the evolution of the probability distribution, just like we make sure that the transition matrices preserve probability because they have stochastic matrices, rows sum to 1. There's a similar constraint for these quantum processes. But basically, it's finite state machines with complex transition probabilities. And they can do all sorts of things. Roughly, though, it turns out that in the finite state case, they're sort of less powerful in terms of the observed languages than finite state machines, classical ones. They're more constrained. Yeah.
Is there anything that you could like get from doing the same thing but on different shapes? Any meaning behind that?
Oh, sure. I mean, different topologies?
Or like, you know, I mean, I'm assuming that you go to wave functions on a sphere because that is
Oh,
the means of measuring things for quantum, but
yeah.
doing the same
Right.
type of thing in different
Right.
spaces with different metrics.
Right, so you've got this qubit, and you think of this as vectors kind of stuck, and so it can only move, it can only rotate, right? Most of quantum mechanics is just rotations in some space. It's kind of boring. So why not do something else? So instead of just having these qubits,
Like if you have a
constraints
machine
of-
that stays
you can use these quaternions. They're other objects that we use now. So suddenly you start kind of realize there's this whole new game. Well, I just went from finite state machines and automata theory. I added probabilities to them. Okay, classical stochastic process. Oh, I let them be complex. I have qubits. Oh, why not have them be quaternions? And so you can just ask. I mean, a whole range of projects here, other kinds of devices. You might want to motivate the invention of them by some practical issue, but if you're a mathematician, go ahead, do whatever you like. Anyway, you know, the word distributions and right. So there's internal sort of quantum dynamics on these qubits, these sort of vectors constrained in a unit circle, and then there's a measurement onto kind of zeros and ones until you get languages out. So yeah,
So, question actually.
sure.
For a little bit of.
Mhm.
See, since they're all complex, how do you know when to stop? Is that when you can have a real number that's like an actual possible realization?
Those are the constraints I was talking about. So there's certain, yeah, not every possible vector is allowed, and they have to be basically, when you multiply them together, you get a real distribution out over the states. So yeah. But of course, then the benefit here is that because they're complex numbers, you can have these interesting interferences. So it's kind of hinting at why quantum computation is such a hot area right now. That's the additional thing. When you move to complex numbers, then you have quantum interference or phase information you can maintain. So what can you calculate, with phase information? Well, we can break all the possible codes, secure, because we can factor large integers quickly. That's the Shor algorithm. It doesn't use finite state devices. It uses more sophisticated computing, like quantum computing devices, but that's sort of where the power comes from. Yeah, so my own interest was just doing the finite state case, trying to think about measures of complexity here first, in terms of quantum processes, as models of real molecules, and as opposed to more abstract quantum database and other kinds of quantum algorithms. So anyway, obviously a huge area just kind of opens out there. But this is a framework where we're trying to think about sort of molecular dynamics this way. So we made just a little bit of progress. Kind of these would be kind of the idea was the kind of epsilon machines for very simple quantum processes, particular molecular dynamics. Okay, sort of shifting gears a little bit. I mentioned Shannon's original papers talking about what he called the rate distortion theory, and there was this problem. He was mostly working in, almost entirely working in discrete state processes, but sometimes he wanted to, he knew people wanted to communicate real numbers over a channel, so how do you do that? So he was interested in this issue of approximation. If I have a real number, what's the best way to code up with discrete codes a real number? So that's led into this idea of trading off the structure of the codes in codebook against the accuracy of and so this has been adapted recently to the setting of epsilon machines. It's also called, in kind of the neuroscience world, called the bottleneck method. And so what you do here is you write down some kind of objective function. In this case, just in terms of informational quantities over your process. Basically, and there are different forms of this, but basically the objective function specifies a model complexity and some prediction error. And then there's this parameter that trades off between these two things, in this case called beta. And then what you do is you try to find a space of approximate models that are the fixed beta, minimize this total information content of the model. Or I should say, this really captures the relationship of the model, the candidate states are, to the process itself. It's like a measure of distance, not really, but between the given process and these effective states or the effective models you're looking for. And in some cases, you can kind of solve this using functional derivatives to find the minima in this. And the space you're looking over are how the paths map to these candidate states. Should it be one state? Should it be two states? Should it be three state? And calculate this out. So what you can do is then actually solve this, in this case showing it numerically. So what I'm going to show you here is the process is actually the simple non-unifeeler source. So I know it's not finite state, it's countable infinite state. And then what we do is you start up at, well, let me say, get this right. So beta here will be evocative to people who study statistical mechanics. This is like an inverse temperature. So the way we think about this is we start with allowing for, let me say what the coordinates are. This is the sort of error in the model, and this is the size of the model. Okay. So what we're plotting here is the trade-off against the model complexity, model size, against the allowed error. The way we think about the process is it's like annealing. We start with allowing a lot of error. So we just have a single state bias coin, and all we're estimating here are the transition probabilities. And then we cool. The slope here is 1 over the temperature. We cool until get at some lower temperature down here, just a couple % error. You have to start using 2 states. You have to start using 3 states to get this error level. Have to start using 4 states to get to this level. And the square box is actually the epsilon machine. So this is this rate distortion curve, and it's trading off model complexity against error. So one way to think about this, you're a designer, and you know, oh, I've got to represent something with a certain amount of accuracy, so what size of model should I be using? Another way to think about it is, I don't want to use an infinite number of states for the SNS, because I know, actually, the chance of seeing 1,000 ones in a row, that's just, who cares? Just throw that away. I'll accept that error. So to the extent this rate distortion function becomes steep, it means that for small variations in the error, you're allowing a little bit of error, you can have a huge decrease in the size of the model, basically from infinite down to 6 states. It's so steep here. So it shows you, so the steep parts of the rate distortion function show you where there's sort of an advantage to using smaller models. And then Shannon's theory lets you sort of calculate these things using, well, more modern algorithms, but basically show how to set up these various kinds of objective functions. And you can do different objective functions. Informational objective functions do have other properties you're interested in. Oh, I want to have unifeeler models or non-unifeeler models. You can put that into that. So this is another sort of approach to sort of inferring epsilon machines, if you will. Yeah.
I was just thinking back to like the space of epsilon machines.
Mhm.
It would seem like you have these candidate machines that are very close to this infinite state machine that someone lives in this space.
Yeah.
Does that lend itself to any ideas of the structure of that space just because of those proximities?
Well, it does give me some picture. I mean, there's still more to say.
Is it really specific for each machine? Like that diagram, or should we be doing those diagrams for families of machines at the beginning? So,
Well, this is a family of machines, right? That were approximates. So all the dots along here, these are all the best causal approximate at that level of error and that size. Okay.
for what data set?
I can make much bigger models at a given error level. That's why this whole region above the blue line we call feasible. I can make bigger models always. Down here, they're infeasible. No such model exists. Right. So this rate distortion curve is the boundary between feasible models and ones you can't implement or that don't exist. So it kind of depends on what the. Well, in this case, it tells you sort of what the neighborhood of the SNS looks like in a kind of continuous way.
Like, so like, the 5 state and the 6 state are really close, 1 state, 2 state are really far. Does that translate into like the space of epsilon machines in that distance at all, or like potential distances, or like should those two be closer if you're?
I don't know. I mean, yeah, if you want to go back to like the previous slide and think, okay, now I allow myself to think about the space of all the processes. Okay, let me think first about the space of all epsilon machines. And then you might be able to use this to sort of connect them up somehow. I hadn't thought about that. I mean, this is a different, this kind of design sort of interpretation. You have this free parameter that you get to choose, the allowed error level. And then that kind of induces a distance.
Yeah.
But yeah, interesting question. So shifting gears yet again. So we talked about cellular automata and a bunch of examples, right? So these are, in the case we talked about, one-dimensional lattices with finite state machines at each site, basically just zeros and ones, and each site talks to its neighbors, looks at its own state, their state, and deterministically moves to some next binary value, just a function, and generate these interesting, or chaotic sometimes, space-time diagrams. Well, it turns out that built into these space-time diagrams are large regions that have the same statistical texture, the same stochastic process. We call those domains, and they're actually invariant sets in the sense we were talking about. So there can be groups of space-time configurations, think of these as patches, such that if I shift in space or I shift in time through this cellular dynamic, they come back to themselves. Exactly the original definition of an invariant set. So one of the motivations for this is, well, first of all, people study spatial systems. However, we think of the dimension of the system as being the number of lattice sites. Each one of these is a degree of freedom, so this is a 287-dimensional system. So how would we ever apply the notions from original dynamical systems theory, right? We study one-dimensional maps, three-dimensional flows. It's all the intuitions and concepts come from these very low-dimensional systems. How would you apply it to a spatially extended system like this that could be, well, on an infinite lattice would be infinite dimensional? I mean, what's the geometry in that space? So, but it turns out you can at least take these ideas. Maybe this really argues why the concept of an invariant set is so important, or invariant distribution too, is so important, because you can come into this and say, oh, give me sets of configurations that are temporally invariant, or spatial shift invariant. And when you do that, and we have an automated way of doing this, and of course we use epsilon machines to represent these textures. In fact, this was the original motivation for enumerating the cellular automata library. The epsilon machine library was to figure out what kinds of, to test 1-state, 2-state, 3-state epsilon machines if they were candidate invariant sets. Very kind of enumerative way. But remember, the invariant set definition takes a set of states, configurations. You apply the dynamic to it, it comes back to itself. That's an algebraic constraint. It's a fixed point equation over sets. Well, you can write that out, and you can try to solve that. So this is what we're trying to do to solve that. So in this particular case, this is elementary cellular automata rule 22. People had studied for years using observed information statistics, saying, oh, it has long-range correlations, it's very complex. Turns out, actually, that it really just has 2 different kinds of particles. So what I've done here is exactly the same space-time diagram. I applied this algorithm that discovered what the textures were, the epsilon machine invariant sets were, and then I make a filter that every time I produce a new spatial configuration, I run this through a little filter that says, oh, you're in this invariant set or you're not. And there are 2 different ways you could not be in the set, and we color that yellow and red. Well, first of all, there's a large part of the space-time diagram that are explained by that texture. Then there are deviations from it, but the deviations from it actually are spatially localized and move around like particles. So you can actually sort of write down it's called a Longiform equation, that kind of a diffusion model for how these particles move around. It turns out that the red particles, when they get close, they pairwise annihilate. When the red and yellow get together, they generate a bunch of other red and yellow particles. There's like an effective chemistry in this. And if I give you what we call the particle catalog with the domains, the particles, and the particle interactions, that lets you calculate any statistic over the space-time diagram. It's a complete description. I'm trying to figure out how to prove it's minimal. I don't know how to do that yet. But so this has been sort of automated. This kind of, you give me a cellular automaton rule, and we kind of run through these tests and discover these space-time invariant patterns. We factor that out, sort of coloring the deviations from the hypothesis that the space-time diagram was described by those patches, those finite information patches. And then you ask, oh, at this new particle level, is there some regularity? In some cases there is, like, oh, purely stochastic motion here. So there's one elementary CA18, it has one particle. They hop around left, right, fair probability, and when they get close, they pairwise annihilate. And that's it. You can prove there's no other structure in this. There's another one called Rule 54 that actually has 2 more levels of structure. You filter out, you try to find, oh, regularities at the particle level. Oh, I see that. Factor that up, and you go up again. Very much like the hierarchical motion we were talking about before for temporal processes.
Are there cellular automata that have infinite hierarchies?
Yes. Yeah, you can embed a universal Turing machine in this, in one-dimensional cellular automaton, and presumably, because of all the halting problems there, the uncomputability, yes, such things exist all the way up, right? Yeah. So this is CA computation mechanics. So an extension of, so we've been just looking at time series, but in fact you can look at 1 plus 1, one space, one time. 2-dimensional space, well, that's actually an interesting question. So one of my former students who was here in this department years ago, 20 years ago now, Dave Feldman, did his dissertation on looking at 1D and 2D spin systems. And in particular, back then we were just using the excess entropy. So the interesting thing that happens when you move from one-dimensional chains, it could be a spatial one-dimensional chain or a time series that we've been working on, you have a 2-dimensional configuration like this. There's no unique parsing of the values, the zeros and ones, or the spins. Right? I mean, if I have a time series, you have a time index. You know, time 13 there's a 1, time 14 there's a 0. There's a natural way to parse it. Here, do I go in circles? Do I go this way and come back this way? So there's a kind of ambiguity. There's no natural parsing. Now we did talk about the bidirectional machine, right? And that was allowing us to break out of this notion of, oh, time always increases or time always decreases. That representation let us go forward. Oh, I want to go back. I want to go forward again. So there's some kind of hint in that that may allow us to deal with this. But anyway, it turns out there are ways of extending the excess entropy over patches. So it's mutual. I mean, we came up with a different notation here. Patches, right? So this is the mutual information between the sort of left half of the configuration and the right half of the configuration, and then we split the height to infinity, so you can define that. There are block entropies, just like block entropies, call them patch entropies versus R block entropies, and so on. And then these scale not as E plus H mu L, but there's another kind of scaling in terms of the width and the height of the patches. The width and the height of the patches. So very analogous. There's a linear asymptote to this patch entropy, just as there was a linear asymptote E plus H mu L for our block entropies. But we have different coefficients in front and different offsets. So these are different kinds of apparent stored information. So now in the world of statistical physics, the main point we were trying to make is that these various excess entropies make really great natural generalized order parameters. So this whole thing that you do in statistical physics, you cobble together your spin system or your molecular system, you sit there and you stare at it for a while, and you kind of come up with, oh, the average number of upspins. Call that the magnetization. That's the thing that really captures when the system is disordered, when it's ordered, and often the order parameter goes through some interesting behavior, a phase transition when you have separating 2 different phases, disordered gas-like solid. But it turns out the excess entropy is a great, almost universal order parameter for picking these things out. So this picture just, typically what people do is use something called the structure factors, which are basically Fourier modes. But you have to know, depending upon what your ground state looks like, so these are ground states of the 2D Ising model, stripey this way, stripey that way, or just a checkerboard. They have different amounts of stored information, which you can pick up with E, but you need to know how to tune the traditional method using these structure factors to pick those out, which sort of begs the question. So our suggestion is just do E first if you want to find out. You've got some new spin system. You want to know how it's ordered. Calculate E. Could be a little hard, you know. Structure factors are good because we all know how to calculate Fourier transform, but that makes a real strong modeling assumption that whatever order you're looking for is periodic. We know there's plenty of order in non-periodic things, so.
What type of patterns doesn't this whole block, or what are they called?
Oh.
Strong patch thing pick up? Or does it seem to?
Well, I mean, what wouldn't
Like
it
these
pick
don't
up?
seem to be like shift symmetry, like
Yeah, I mean, but they could also be, kind of like,
spirals or rotations.
one wild card type of things too. We can certainly do that. Yeah. I mean, when you're using this as some kind of indicator of, so this is the coupling strength. So going over a family of spin systems varying the nearest neighbor coupling strength. You can pick out, so this is 3 bits of excess entropy. That means there's some sort of 8-state thing underneath it. But there could also be stochastic versions of that. We studied just the ground cases that were periodic.
Okay.
But it's something like Penrose Tally or something. You
Yeah.
don't necessarily
Right.
expect this to be
Right. But you
Or even
might
just
want to
some-
have the analog of the entropy rate, which is a spatial entropy density. We can calculate that, and we did that for these. So So actually, tilings, that's a whole other interesting area.
That's what I was wondering if
yeah.
you could use like this, I mean, there are only a finite number of symmetries of a plane, so if you can somehow match your testing to those.
Yeah.
But like, if you had like, just say like,
But it depends
given
on.
your square, like if you had like
Mm.
black dot and then border white, border black, just that rotational symmetry, how
right.
would that
Good question.
fit that? Okay.
Yeah.
Okay.
I mean, I think you would pick it up, but you would still have to come in and see what the symmetry was. It's just a scalar number, or you have a couple here, so maybe it helps distinguish these things. But there might be, I mean, just like you can have a large epsilon machine with some 2.5 bits of statistical complexity and a small one. They're detailed. When you just use scalar numbers, so these structure factors and excess entropy, so-called order parameters, are just going to give you a hint that there's something interesting going on. I have this big system with lots of parameters. Basically, you can just simulate it a bunch and see where these numbers say, oh, it's interesting over here. So, yeah. But research problem. No way am I saying that I'm just introducing a problem here. And then this paper down here is just the first cut at it. And so I should probably speed up here a little bit just real quickly. So imagine we don't know what the mapping is. So Chris Strelioff and I are using some of the Bayesian methods to look at, trying to design an algorithm that would move through the space of partitions. So this is actually the logistic map. And we're looking at the space of binary partitions, where D is where we put the partition down, right? And we studied everything at the generating partition where D was a half, and that gave us left, right. But here we're looking now at the entropy rate and the actual order of a Markov process as a function of the decision point. And so what you see is that at the generating partition, the entropy is maximized. So it's kind of like a little principle that says, oh, over the space of partitions, over the space of instruments, what you should do is choose those partitions that give you the most informative, most entropic measurements. It's like, use all the information that's there. Don't throw it away. I mean, of course, if I put it off the attractor, well, that's kind of dumb. It's like, I'm not getting out of bed today instrument. I don't want to deal with the world. But there's also another maximum here. Turns out this is the inverse iterate of a half. And halves give the same symbolic dynamics. And then at those values, what you see is you have minimum order nearby. So sort of like use all the data, nothing but the data. So there's some hints there to how you could algorithmically design good partitions. And then in terms of this kind of survey of what we kind of currently know a little bit of, I mentioned thinking about complexity entropy, structural complexity, and entropy as a measure of randomness as kind of stand-ins for thermodynamic macroscopic parameters. So the thing here is to take some class of systems, spin systems, logistic map at different R values, tent map, even the space of epsilon machines. What's the diversity of information production, entropy rate, and corresponding structure. So we're kind of taking this complicated space that's really high dimensional and projecting it down to two scalar numbers. Okay, we're throwing a lot out, but maybe it hints at some organization. So you might think, oh, down here with low entropy rate or low randomness, that would correspond to crystals. This might have high randomness would be like gases, and so it's kind of like a thermodynamic phase diagram. So just to get started, we've looked at logistic math ad nauseum. So here's the bifurcation diagram, function of R, rendered in terms of the excess entropy and the entropy rate. So here's the entropy rate going up to 1, and then here's the excess entropy. Going through period doubling and stepping up. So we have period 2, period 4, right? 2 bits of information, period 4, period 8, and then this. So the idea here is just to do a cross plot. Drop R, do an implicit plot, and do a scatter plot of amount of memory, E, and amount of randomness generated. So that's the complexity versus randomness, complexity entropy diagram. And what you see is that there's actually quite a bit of regularity. So all of the periodic processes, of course, are here. So period 4, whatever. But it's not a full scatter plot, right? There are whole regions of information processing, storage, and random generation that the logistic map can't do. There's even kind of a lower bound here. What you might posit as a smooth curve, well, we can actually derive that. There's this lower bound, and there's kind of an approximate upper bound you can give a functional form to. We also know that the logistic map, as in terms of the bifurcation sequence, is self-similar, right? Where 2 bands merge going up to 1 band, it sort of looks like a piece of that looks like 4 bands going to 2 bands. And so, in fact, we have these scatter plots actually lay over each other if they're rescaling right. So just giving us, one picture summary of the range of information processing the logistic map can do. Do the same thing for the 2D easing system, which is one of the first simple systems that was analyzed for phase transitions. There's a critical temperature above which there's so much thermal noise the spins don't align, below which there are these large patches of seas of upspins and seas of downspins. And right at the critical temperature, there are these very long-range correlations. Patches of upspins, patches of downspins can be arbitrary spatial size and correlated over arbitrary long times. And so as a function of this was the temperature. We just looked at the excess entropy versus the entropy density, or entropy rate. We get this picture. This is where the phase transition occurs. For those who know the lore of the 2D spin easing system, various thermodynamic quantities actually diverge, but the excess entropy doesn't. So that's a bit of a puzzle. We don't have critical exponents. E is kind of just smooth. There are other spin systems where it diverges, but this is kind of curious. It doesn't actually diverge. It means in some sense that the phase transition is simpler than you'd think.
Is there a classification of first order or second order phase transitions in terms of excess entropy? Or is that...
I don't know. Good question. Yeah. This says it's picking something else up besides that kind of criticality. So, right, it might be a much higher order type of critical exponent for a system in which it diverged. It doesn't here. Which, I don't know, well, this actually doesn't bother me because when I do simulations of the 2D spin system, it's always pretty noisy around the phase transition. You're really looking at it to see that it's infinite. I know other systems that kind of lock into order and structure from a gas phase. And that's a really big change. And I expect the transitions there to be more dramatic. But interesting set of questions. And it does tell you that the system is somehow storing some more information. And maybe if we ever figured out what an epsilon machine is for two-dimensional spatial configuration, maybe causal state diverges, right? Could be, right? Because this is just a lower bound on statistical complexity. So, and then finally, our epsilon machines, just a survey, excess entropy versus entropy rate. Again, it's not a big scatter plot. So this is one-state machines, or just 3 dots, up to 5-state machines. And it's actually topological epsilon machines, just calculating h, mu, and e, and it's actually quite structured. There are families of machines you can pull out here that kind of bound the range of information processing. Also, you notice as you get more and more random machines, more and more higher and higher entropy rate, there are fewer and fewer machines kind of going into the IID process limit here. But again, that's because of the topological machines. So, yeah, so it's structured. These various towers, we can explain these. There's a lower bound we can derive, there's an upper bound, and so on. Fixed number of states. So another view of the space of processes. These are all like, holding the crystal up and looking at it from different directions. All hints that the space of processes is quite structured.
What are the lines of constant h or
H mu?
entropy rate corresponding to? It appears you
Yeah, the towers, yeah.
It's relatively isolated there with a window.
Right, that's another thing. It's like, good question.
Would it fill in more with like higher end? Would it fill in completely?
And these are all binary.
Yeah, these are binary topological epsilon machines.
It has something to do with the topological machines only can have half probability or something like
That's why they're certainly handy.
So notice that the towers, well, I'll pick up, I won't give you a complete explanation, but notice that there's some, in this case, a 3-state machine, above which there's a tower, above which there's a tower. So sort of what's going on here is you're splitting states and then adding transitions in that don't change the entropy rate, but add more probabilistically distinct causal states, more complex. Okay, now you should object because what I'm plotting here is E, so it turns out that's harder to do. We do have C mu versus H mu, and then I can go point out things a little more structurally. So I'm a little bit hampered by this being E because of the indirect relationship to structure, internal structure. But there's a paper with Carl McTagg and Dave Feldman. We do show you roughly. I mean, we didn't do a complete analysis, but there are like 3 or 4 families we could pull out and structurally show how they're parameterized and get those E, H, and E pairs exactly. So there's quite a bit of structure there, and more than we've actually described even. So. Okay, well, that was kind of a survey of some things that I would have loved to go through that kind of we've worked on over the years. People are now using this in a lot of different domains, and let me not go into a lot of, a similar sort of even brief explanations of them, except maybe to mention just one of them. This is kind of a recent one done by a group in Japan. They're looking at the conformational dynamics of these large proteins. And the way they do this is they isolate them. Sometimes they do this with DNA things, sometimes with these proteins. And what, at least up until recently, what they've been trying to figure out is they can shoot in a laser and look at the fluorescence signal coming back out. Or sometimes they look at electron transport. There are a couple different methods for doing this. And presumably these scalar signals coming out of proxies for different configurations of these big macromolecules. So in the literature up until recently, there was all this interesting, after the experiments were described and molecule data taken, usually the discussion section of papers was all this narrative about, the effective states of the process. In this particular one, we see 3 effective states over here. So what they're doing now is, in fact, taking the fluorescent signal coming out, the time series, and just building epsilon machines. Like this, they get fairly big ones, but they're now talking in terms of this. Now they have this more detailed picture of the hidden dynamics in terms of these causal states representing different conformational structures. So this is like a small little industry now in single molecule spectroscopy doing this work, using these methods to get a more structural picture of the internal dynamics of molecules. And of course, that dynamics is exactly what makes proteins functional, how they move around. So this is a key thing to figure out how proteins can be functional and do what they do. Just in its earliest stages, but
It would be really helpful because then when we do a simulation, we can get another Epsilon machine. and
For example, right.
compare it against.
Right.
Yeah, the experiment, there's all sorts of experimental issues here. So with the simulations, you can,
Which I don't know if they're, I think they're starting to do that, but yeah, so. And then let me just, last few minutes, pick a couple of the things we're sort of currently working on. Actually, asked really interesting questions. So even the previous examples, I think almost every one of those examples of what we knew, in fact, there's a lot we don't know. So even those were interesting research projects. But there are things we're now focusing on. So let me just mention a couple of these. So we talked about, Varn talked about this epsilon machine spectral reconstruction, right? Go from some material, stick this in your favorite X-ray diffractometer, vary the angles and look at the reflected energy from that, and you get this picture of this different kinds of peaks, so-called Bragg peaks, but often there's this broadband background that the experimentalists used to just throw away. It was a dirty sample. And then he, in the second lecture, talked about how we can get the epsilon machine from that and then interpret different cycles in here as periodic order along one direction in these crystals. Allowed us to talk about multiple crystals and different kinds of faulting structures, which are shifts between these causal state cycles between one and another, and so on. Those things. But now imagine that this description is a good way of describing these complex materials. If you have the epsilon machine, you can calculate now, in principle, various physical quantities, like the resistance or the band structure and so on. So now imagine you kind of mess around in model space here and go, oh, this one might actually have an interesting band structure, be an interesting semiconductor. And then you can sort of go back. Of course, you have to convince the materials growers to make that. So it's an interesting question. The nice thing about this, especially with the epsilon machine, is you can calculate properties over whole classes of realizations. So it might be a little more robust. So even if you don't get exactly, this particular sequence of orientations in the layers you're growing, it might be fine. You could still capture the basic properties you were interested in. So then go back and sort of design your own semiconductors. Yeah.
Have you talked to Julia Vialli's group in chemistry?
Not yet, although.
Because they're.
Yeah.
I guess they're working on materials that have varying levels of thermal conductivity versus electrical conductivity to try and get good materials for energy production.
Well, we're presumably collaborating now because we just are putting in a preliminary proposal, but the discussions haven't gone anywhere near far enough along these lines. Yeah. So, yeah.
I don't really know how the crystal growers do their thing, but is there any way that you can actually use the machine to build materials?
That would be interesting. At least after you go to live in the Silicon Valley and you go to Maker Faire and all this stuff is so rapidly changing. You sort of imagine with nanotechnology, you should be able to just make the 3D printer at the nanoscale that does this. So yes,
And,
wouldn't that be great?
Program
Absolutely.
on the machine and say okay,
Yeah.
give me 3 layers in this cycle.
Exactly.
Transition.
Yep.
The benefit of the epsilon machine I can see is that you can do it stochastically.
Yes, right.
You don't-
Whole classes.
You don't have to manipulate individual layers. That you could just anneal at a certain temperature.
Exactly.
And it would give you certain orders.
Just with the probability
Yes.
distribution.
Just
Right.
the correct probability
Exactly.
distribution,
Yeah.
which would give you the right thing that you need.
Yeah.
Because all
So
the properties
instead
are
of-
the same.
So instead of doing the nano manipulation, you just
Feed it the machine and it gives you your material.
Yeah, or maybe that means you just
Different
change the
probabilities.
density or the temperature or the
Density,
sputtering
temperature,
angle, or
pressures.
there's all sorts of different techniques that people use. Yeah, exactly.
to do it,
Right.
do it stochastically.
Yep.
rather than
For whole classes of realizations, exactly, and then you kind of guarantee. So the idea here is kind of describing the stacking. Well, you can go from this to basically defining a lattice, and then you solve your Schrodinger equation on that to get your physical properties, and then study that. Hopefully there'll be some direct analytical way of doing that, but let's see. Just do a realization. You have your lattice. Do your solid state physics on it. But hopefully we'll be able to connect up some of the informational properties directly to the physical properties. And then, search the space. Oh, that's interesting, and then go back and try to grow these things. So that, a little speculative, but I think, at some point you have to throw your hat in there and say, okay, in 3 or 4 years we should be able to do this. Okay, moving on. Right, so novel materials. Well, I just said this, right? Somehow we can turn the emissary algorithm around to design these different kinds of polytypes or maybe other higher dimensional materials. I wanted to mention real quickly, and I'll do this in a terribly superficial way that will frustrate Paul, but basically as a product of this class, as he was sitting quietly in the back, we came up with a really amazing way of giving exact closed form expressions for all of the information measures we've been talking about. So I'll do this in a terribly simplistic way, partly for time. So how are we going to do this? Well, remember how useful the mixed states were in kind of summarizing things. And then it turns out that because if you use the mixed state presentation, there's a way of looking at the eigenspectrum of the epsilon issue, looking at the eigenvalues. And I'm just going to give the eigenvalue version of this. So remember that absolutely tortured derivation I did. It's the longest derivation of the class, where we derived how to get the entropy rate estimates as a function of L. But the punchline was pretty simple. What we do is we be very careful to look at how an initial distribution gets pushed forward through the mixed states to some time later. And then we just look at the one-step symbol uncertainty. So everything boils down to tracking the mixed states. Well, those are given by some transition matrix, particularly some power of a transition matrix. So because we have the mixed states in there, we don't have to look at the observed process, and we just push through the internal states this way. Well, it turns out that in the different fields, like in quantum mechanics, people know about these methods. You can represent functions of a matrix, especially when they're diagonalized, as functions of their eigenvalues times some basis vector. So in this case, the powers of the matrix, here you can show what you do if I'm interested in the elf power of t. All I have to do is raise the eigenvalues to the elf power, and then I have these so-called projection operators that tell you what subspace. They're like the generalization of eigenvectors, subspaces that are invariant in some sense. So you can decompose powers this way. Well, that's nice. If I have these eigenvalues, suddenly all I have to do is take powers of them and then calculate this basis set of projection operators. So that's what they look like down here. But let me move ahead. The net result, and there's magic that happens between that and this, but just so you see, mostly it's a visual impression. Right, the excess entropy one way we had of looking at that was this infinite sum of the approximations as they're converging down to the true H mu. Right, that's the excess entropy converging from above. Small l, more random than it really is. We sum those things up, and that should be giving us some measure of correlation or memory, where you can actually write out explicit closed form in terms of the eigenvalues. So you start with the asymptotic measure. These projection operators, these submatrices, are implicated in this, and then you look at basically how mixed states hit the individual symbol transition matrices and generate zeros and ones symbols. So there it is. It's finite. It's on the page. Before we were doing numerical approximations or maybe efficiently using mixed states, but in fact, because it really boils down to this realization, it's just powers of the state transition matrix, internal state transition matrix, mixed state. You get this finite thing. Same thing for the synchronization information, finite form for this. But now, the only difference here, it's a rather similar formula, summing over all the eigenvalues that are not 1. It's a relaxation where the eigenvalue equal to 1 is the association with the asymptotic state distribution. But we just look at the entropy over the mixed states themselves. So there's an averaging there. Same thing for the transient information. So there you go. Nice closed form thing, which we're currently writing up. So.
Is the use of direct notation just an analogy, or is it actually a group space of some sort? Like the prime?
At this point, just think of it as a nice way of keeping your rows and columns organized. But in fact, yeah, it's borrowing actually all of that because it's mathematically appropriate, and there's good reason for that. So it looks a lot like yeah. So I should kind of hurry up here. We're down to the very end. Okay, I can't help but. So another thing, and this is, we've been talking about epsilon machines. Those describe behaviors and distributions over behaviors, the word distribution. That's a set of behaviors. What about mappings of those sets to other sets? So there's a whole other project going on here. We call them epsilon transducers. They're sort of minimal optimal mappings from one process to another. So And there really are models of kind of memory-full communication channels. We have some input process here, and it's generating some output process, and we're asking the same question that parallel the epsilon machine. What's the optimal, minimal presentation of a mapping that does this? What are the useful informational invariants or properties of this? What's the minimum amount of memory you have to go, from the even process to the goal mean process? So Nick Barnett is working on this. He's in the math department here. And so we have input process and output process, and most of this theory is talking about joint processes, joint input-output symbol processes. And maybe I'll sort of finish sort of graphically here. Here's some examples. Let me not go through in detail, but here's the identity channel. Input word of length 8 to output word. Well, no surprise, the identity channel has no memory, just one state, just the identity function. Here's maps all processes to the fair coin. So whatever word comes in maps to some other random thing. So we have a scatter plot. So these are the two extremes. But it gets more interesting. We call this the Z channel, this guy over here, input word to output word. And what it does is it transmits zeros, but anytime a 1 comes in, it's a fair coin. So there's certain restrictions. We're going to end up with the Sierpinski gasket fractal kind of pattern. I'll explain this to you. Those are the previous three. These are all memoryless channels, single transducer state, causal state. We can also do a memoryful channel. The easiest one is delay by 1. The symbol comes in at time t, doesn't show up in output till time t plus 1. And I don't know, maybe you can convince yourself what you end up with is the shift map from inputs to outputs, which is delays by 1. But then all hell breaks loose. So this maps the even process to a fair coin. You get this interesting sort of fractal kind of picture here. Self-similar. The two states, I forget which is which. One is purple, one is green, when they're being exercised in the function. Feedback, NOR. So it's just the NOR of the previous output and current input. It's interesting. Fractal kind of picture. And the fractal dimension of this will be one characterize the complexity of the function and so on. Okay, well, I have gone over, no surprise. So another direction we're moving things in is not the learning channel, which is batch. The world behaves, I get some data, I build a model. What's of course more interesting, so we've just been studying the world, producing a set of observations, building a model. But what happens if you make some decision based on that, that then you take an action that affects the world? I mean, this is like one of the holy grails of engineering and all sorts of design. Why is this difficult? Profoundly difficult. It's because when you take an action, you affect the world and its statistics, which means you have a new modeling problem. But then you learn something, but then you can take another decision which affects the world. So this is a huge open problem. In machine learning, in control theory, engineering, not really well laid out. So we're trying to approach this using some of the ideas of computation mechanics. Oh gosh, so a fun one, if you'll bear with me here. Another interesting project we've been looking at, this is with Sean Whalen. He left here and went off to Columbia. He was in computer science. He's looking at the evolution of language. But a very simple way to think of this is sequential inference. So we all know that language is sort of fraught with errors, right? So this is, kind of reminds us of this game of telephone. I tell you, you afraid, you tell someone else, and then by the end of the chain, this phrase has morphed, and it's usually employed in grade school to let kids know that language is fraught with misinterpretation and error. But it's not. That's an incomplete picture of what's going on. Because as a human who's trying to understand and then trying to be understood, it's not just the accretion of error. It's actually gets mapped back into something understandable at each stage. So it's actually a balance of those two things, like any language system would be. There's a certain amount of novelty that one is communicating, but it can't be too novel because you still have to understand it, and then people try to map it back down so they understand it. So what we were looking at, and it's kind of a famous apocryphal example back in radio, World War I. Send 3 and 4 pence, we're going to a dance, when in fact the guys in the field said, send reinforcements, we're going to advance. It's kind of morphing a little bit. So what we do here is we look at a model, we generate a string, here called alleles for evolutionary reason I'll mention in a second.
we have a realization, we do an epsilon machine inference, we use that as a new generator, and then we infer again. So it really is this sequential communication of knowledge, where knowledge is the structure of the epsilon machine. And the connection to the mathematical theory of evolution is what's called genetic drift. And so what's going on here, the way to think about this, the simplest model, which goes back to the 50s, and this population dynamicist Mutu Kimura, is the idea is at the level of some molecular evolution. Imagine you have a biased coin. So start it as a fair coin, but I'm only going to flip it 10 times, and I give you that realization. Well, because it's a stochastic generation, there'll be some variation. That length 10 string isn't always going to have 5 heads and 5 tails. It might be 6 heads and 4 tails. So, but then take that empirical measurement of the bias, and that becomes your new bias. So this is a model of what they call genetic drift. You're accumulating mutations until finally a population, say, loses all of it, or you get a completely biased coin. And then as soon as the bias of the coin is all 100% heads, every future realization is just going to be heads. So the process shuts off. So that's what we did here. This model of the evolution of language is, well, you can guess it. We don't use biased coins. We use memorable sources. We don't do IID biased coins. We have epsilon machines that generate a finite realization. And then the inference process not only is estimating the bias, but also the number of states, and that can change over time. So this is what it looks like. We can start with, here's a golden mean, we start the even process, and then it varies around and shuts off, then finally it goes down to all heads. The golden mean start as the initial process instead of a biased coin, ends up going down here to period 2. Then this is just the biased coin that goes all the way up here. And so we monitor this in the complexity entropy diagram. Even though it's moving, it's a diffusion through the space of all epsilon machines. You can see these subspaces. So this is several hundred realizations starting from the golden mean process, and it kind of hops around these different subspaces. And then these coherent subspaces here, they actually correspond to a particular topology, and then the variation is just the sequential inference making statistical errors in the estimate of the transition probability. So you get slightly different complexities and entropies until you can change subspaces when the inference algorithm sees a realization that doesn't justify having too many, 5 or 4 states, maybe a 3-state thing. So you would go from here down to here. So you can actually study this evolution of structured processes. So we're trying to push this in the area of elaborating genetic drift theory to memorable sources, but also thinking about this as an example of the evolution of natural languages. So here's a fun little example of this. Not quite the same thing. I don't know if you've gone to translation party. So what you do is you type in a phrase, and then it translates to Japanese, and then translate the Japanese back to English, and then translate the English back to Japanese, and so on. So you type in your phrase. My talk is almost done. Hit find equilibrium, and it goes, oh, my talk is almost done. I don't know how to pronounce that. That's the Japanese. Most of my talk was done. Japanese. I was almost done. Japanese. Little had been done. Little had been done. Little had been done. So that's a kind of evolution. So let me, I'll skip over. I've been interested in well, I think as a physical scientist, you're always kind of puzzled when you talk to biologists about where does selection come from, natural selection come from. So we've been studying for a number of years a soup of little epsilon machines, little epsilon transducers that when you compose them, they make children. They're functions, as I said before. You compose 2 functions, you get another function. So we're studying the evolution, pairwise replication. There's no selection in here. It's just who can make more of whom. And the interesting thing is that they form what are called autocatalytic sets of mutual self-reproducing networks. A interacts with B to produce C, interacts with F to produce G, interacts with Q to produce A. And it turns out that these networks are more stable than the individuals. They have to participate in these networks. So the population of them gets structured into these autocatalytic networks, and then the very survival of the individuals depends on how they participate in the network. That's the selection pressure. And this is sort of biology and chemistry-free model of the origin of selection.
It kind of matches Stephen Jay Gould's idea that selection works on various levels, not just on
Yeah.
one.
Yeah. Well. So the interesting thing here is the soup. We call it the finite process. The soup, the population, the individuals turn over to be those that can participate in these autocatic networks of self-reinforcing reproduction, there's this new level of organization, which is the network itself, and then it turns out that you have different networks competing with each other. So it's actually a three-level system and spontaneous. There's nothing else. There are many other models in this area called artificial life where people put in various constraints to get that type of multi-level emergence. This just happens automatically. And it's a really simple system. It's just a gas of finitely specified functions. You just compose them. It's almost a pure mathematical model.
How do they move?
They don't move, but they should. So that's the other thing we're looking at, is how they can move and make. But I say gas, I didn't mean in the kinetic sense. I mean they can randomly interact. In the
How do you program their hash?
function composition, I have a transducer. Right? Each transducer has an input string and produces an output string.
Even what with TP versus
Right,
TA,
so
like why are those interacting but not TP? Like why do they spatially?
Oh, that's okay, right. So I'm skipping over a bunch. There's a simple one-step replication. Population, say 100 of these machines. You pick two, A and B, and compose them. They make C, put C back in here, and then you randomly pick one and throw it out. So the population size is constant.
Okay.
That's the only thing. We have structured individuals. There's no mutation in this model. The amount of randomness is the randomness in each individual, and that gets created.
Yeah.
The only structure is that they're structured functions, and so it's really a self-organizing system.
Based on their entropy or complexity.
I'm not showing you the plots, but we do look at the ways of monitoring the spontaneous organization in terms of the entropy of the networks, the distribution of complexities of the individuals, and you can sort of make a little more quantitative the thing I just said before.
Or do you put in lots of state machines and let those be in there?
Yeah, we'll start with 300 two-state machines randomly selected.
Okay.
Yeah. And then very quickly, when you compose an n-state machine with an m-state machine, typically you get the child is m times n states. So the individual complexity could grow very, very large, exponentially fast, geometrically fast. But what happens is that they don't. Because those much larger machines, the larger the machine, the more restrictions, the less well they play with their friends. So the really complex machines that you could make can't participate in these mutual networks of self-reinforcing production because it's like input domain, output range. They don't match with other functions in the soup. So they get pruned out because they're not interacting.
That's very fun.
Yeah. So, okay, punchline. That's it. Really the last slide. Thanks for bearing with my over-planning. So if I want to leave you with one message, is that there's a way of thinking about structure. So, and I hope this notion of information and intrinsic computation suggests another way of thinking about information processing in the world. So the kind of buzz phrase is how nature is organized, structure, symmetries, and so on, is how it computes. It's a different notion of how systems compute, not based on looking at these current digital technology paradigms, but really thinking about information processing in nature. So I'll quit there. You've been extremely patient, not only this lecture, but through both courses. So stay in touch. And I guess I'll see you all Saturday. And those in the class, you have evaluations to fill out, as if you didn't have enough. Thanks.